There we go. And that. Okay. So how many people here use any kind of AI or machine learning or anything like that? Okay, cool. So all the hard questions are going to go to this corner. So my name is Laurence Moroney, as introduced. So I work on TensorFlow as part of the Google Brain team. We've got two people who our jobs are to be what's called scalable developer advocates, which means we produce videos, we do blog posts, we speak at conferences, all that kind of thing. If you know Josh Gordon, he's the other one. And so I run the TensorFlow YouTube channel. So please subscribe to that if you haven't done so already. We need all the subscribers we can get. But we just crossed 50,000 subscribers today, which is really exciting. But tonight I'm going to be talking about really mobile machine learning and like AI in the palm of your hand and how TensorFlow fits into that picture, which is, I think, one of the most exciting parts of the whole thing. But first of all, when I do it, I always like to talk about what AI actually is and what AI isn't. And like all you got to do is like there's a small search engine called Google. Anybody heard of it? And if you Google for artificial intelligence, you'll see results like this: robots will destroy our jobs and rise of the machines. The future has lots of robots and few jobs for humans. And it's a lot of doom and gloom. And I think a lot of this fundamentally comes from the fact that AI is misunderstood. It's also one of those really interesting technologies in that science fiction writers have been writing about AI since the dawn of time. Technically, the first science fiction novel ever written was Frankenstein by Mary Shelley. And when you think about that, that's a novel about artificial intelligence, that somebody creates artificial life, it becomes intelligent, and then goes and kills everybody. And so there's a lot of negativity around AI, and I think we've done a bad job as an industry in really trying to help people understand what AI is, as opposed to what it isn't. And, we see other things like our good friend Elon Musk tends to warn about AI being humanity's biggest threat. Meanwhile, he's building AI into all of his cars. And then, of course, my personal favorite is an advertising agency in New York, just to labor the point. They did a search and replace with the words artificial intelligence and demonic possession. And you end up coming up with highlights like this one, demonic possession helps advertisers be more compassionate, But my personal favorite is demonic possession now fits inside a USB stick. So be careful with those USB sticks you pick up in Starbucks. And so, and then another one of my personal favorites, the biggest threat to artificial intelligence is human stupidity. And it's something that I always like to say is that we've got a lot more to be afraid of from biological ignorance than we do from machine intelligence. And all you have to do is turn on the news and you'll see that's true. Okay, but what is AI and what's it? Oh yeah, one more. And this is one of the positive ones. I spent a lot of time in the UK, and one of the things that when I was in the UK, when I was doing a talk similar to this, I just searched a whole bunch of UK newspapers. And one of the things that the folks in the United Kingdom do that I think is really good, that one of the things their government has been doing is to focus on how AI can impact the economy and how the country can ready itself for the AI and machine learning revolution. And a lot of that then ends up running through the pipes and coming out in newspaper headlines. And we start seeing things like, UK firms expecting AI to transform their industry, it'll impact the future, coming health revolution, all that kind of thing. And it's interesting that their newspaper headlines tend to be a lot more positive than ours in the US. I'll admit I haven't done a survey of ones in Canada before I came. I apologize for that. But, just go do a search for like newspaper headlines and what they're talking about in AI. And, that will tell you how good a country that you live in. Okay. So with us, though, with Google, we've been working on AI for quite some time, and we open sourced TensorFlow back in 2015. And there's been lots of great results of what people have been doing with TensorFlow since then. Things such as, if you're familiar with AlphaGo and the game of Go, that there was a Korean champion. I know it says Chinese Go master in that headline in the top left, but he's actually Korean, Lee Sedol. And AlphaGo beat him a couple of years ago, and it was really cool. I was in Korea at the time, and everybody went crazy. But it's more than just playing games. There's things such as, for example, diagnosis. There's a thing called diabetic retinopathy, whereas you can take a scan of somebody's retina, and there's so many diseases that can be detected from that, including something called diabetic retinopathy. Now, it takes a skilled optometrist a lot of time to scan one of these images and make a diagnosis, but we actually built an AI that can do it in a fraction of the time. Now, this isn't to compare an AI with an optometrist. This is an AI to help an optometrist. Because if you can do something like this, now an optometrist can see many, many more people in the same time as they would have seen one pre-AI. So that's a lot of the theme of what we've been working on, is it's not about replacing what skilled people can do, it's about enhancing what skilled people can do. Okay, so what is artificial intelligence? So I'm talking about it a lot, but how we at Google talk about artificial intelligence, very simple, the science of making things smart. And we have this website, experiments.withgoogle.com. Go take a look at it. There's some fun stuff you can read about and some fun stuff you can learn about on there. I'll share these slides with the group, so if you miss a picture or something like that, they'll be shared with the group later on. Okay, now machine learning tends to be used synonymously with artificial intelligence, but it's slightly different. But machine learning is an approach for AI where computers can learn from experience to find patterns in data. Okay, that's a bit of a mouthful, and I like to talk about this part from a programmer's perspective, because I guess most of us here are some kind of coder in some form, right? Any non-coders here? Okay, a couple. That's all right. And so I like to talk, first of all, when you think about traditional programming. Okay, in traditional programming, say I have a scenario, and my scenario is I want to identify spam in an email. Well, what I do, I have a lot of rules. If this, then that. If that, then this. While this, do that. Those kind of things. So, for example, if it's a spam and it contains free credit, or we've detected suspicious activity on your account, that kind of thing. An email, those kind of words you could match with, and it might be a spam or it might be a phishing or something like that. But it's kind of hard to do, and it's kind of hard to catch them all. And a lot of the people who write these spam messages are not very good at spelling. So you got to kind of catch up on all the different possibilities of spelling and all that kind of thing. So you end up with a very difficult scenario to be able to come with, to say, like, if I do traditional programming, if this, then that, to say that this is spam or not spam. Or another example is that the eagle-eyed amongst you might have noticed I'm wearing an Apple Watch. And anybody got an Apple Watch? These things? Smartwatches, okay. These are terrific if you do, and I bought one of these for doing fitness. And the activity recognition on these is terrific because this watch knows when I'm running, it knows when I'm walking, it knows when I'm biking, all these kind of things. Now, think about that from a programmer's perspective. Okay, let's just say comparing walking and running. Okay, so how would you do that as a programmer? You might go based on the person's speed, right? If speed is greater than something, then they're probably running, otherwise they're probably walking. But then what happens when you're running uphill, right? Or you're walking downhill. And all those corner cases and all those difficult things, that it ends up being very infeasible for you to write traditional code to be able to detect these kind of things. So the idea behind machine learning and what the folks at Apple have done with this is that they've had millions of person hours of people doing different activities, like walking and running and skating and biking and swimming and all those kind of things, and effectively saying, this is what walking looks like. This is what running looks like. This is what biking looks like. And using those to train a model, and then in future, then inferences run on that model. It's like, I'm generating a bunch of data right now. What am I doing? And then it's giving me back saying, that kind of looks like running. And that's really, really difficult to do in code and traditional programming. And that's the idea behind machine learning. And that's what TensorFlow we've built to be really strong at. So the idea is you classify something, you compute the errors, and then you change and continually iterate and improve. Now, I like to look at it like this, that this is traditional programming. So traditional programming coding is you give it rules, you give it data, you get out answers. So for example, like if I was classifying activity or classifying something that's an email, the rules are my code, be it Java, C# or C++ or C or Python or whatever language. And that's why we as programmers tend to have a career, because we become really good at interpreting a problem and writing it using those rules. And then you have data that gets passed into that. For example, if it was classifying an email, the data is the email itself, right? If this contains special offer for you, or if this contains insert medical term here, or insert drug here, that kind of thing, then it's generally, so that's how you detect a spam, and this is what traditional programming looks like. You give it the rules, you give it the data, and then your compile program gives you the answers out. The whole AI and machine learning revolution is this. It's very similar, but we've just twisted the axes around a little bit. So instead of you giving it the rules and giving it the data and getting out the answers, you give it the answers and you give it the data and you get out the rules. So for example, when I was talking about like this watch, what Apple did when they were building a watch like this one is they got thousands of people to spend many hundreds of thousands of hours doing different activities, and that's providing the answers. You know, all of this data that I'm giving from this person running around the block, that's running. All of this data that I'm giving you from this person walking around the block, that's walking. They gave it the answers, they gave it the data, and out of that they get the rules. And this is a very simple switch that ends up opening up massive, massive new scenarios for you as developers. And, you know, to me, I like to look at it as the third great revolution in my career. The first great revolution, I came out of university in the early 1990s, and the first great revolution was the coming of the web. And that was like, hey, everybody had desktop computers, they had things that were running in isolation. There were ways that you could connect, but there was no standard way. You'd write your own protocols, you'd maybe write your own servers or networks, but then the web came and there was a standard thing, and there was a thing called a web browser. So now programmers had a new scenario that they could build to, and whole new industries opened up as a result. Amazon, Google, you know, all of these things happened because these new scenarios became made possible by the advent of the web. The second great revolution in my personal career was the coming of the smartphone. Now you have this portable device that's connected and has a whole bunch of sensors like location detection and cameras and all of these kind of things. And that opened up lots of great new scenarios. For example, Uber. I know Uber isn't in Vancouver, but we're all familiar with Uber. You know, so the whole idea is like standing on a corner waving for a taxi went away, and the ability to call a car came along. Or Instagram. You know, how many times would you thought of you taking a picture of your breakfast and then millions of people would like that and you could become a superstar? It's all of these scenarios became possible because of these revolutions. And this to me is the third and possibly the biggest. Time will tell when we look back, that this becomes a new way of developing new scenarios that weren't previously possible. So things such as this became possible because of this programming model. And what else becomes possible? I'll share one project that I think is really cool, and I have a video at the end if we can get it to run. And so in Tanzania, in Africa, there are farmers that grow various different crops, but almost every one of these has a backup crop, and this backup crop is a crop called cassava. And the cassava plant is really interesting. So if your primary crop fails, cassava is a very hardy crop. It's not very good to eat, you know, that kind of stuff, but you won't starve. You'll always have some cassava. You'll grow some other crop for profit. You'll grow some other crop because it tastes better or is more nutritious, but you'll always have cassava as your backup crop. But like any backup, if your backup fails, you know, you're in big trouble. So with the cassava crop, one of the issues is that when a cassava plant gets diseased, by the time the human eye can detect the disease, it has probably spread to all of the plants nearby. And its early detection of a disease is vital. So we worked with some companies in Tanzania, and I think it was Carnegie Mellon University, to put together this app, which works and it runs on a mobile phone. And the idea is that we trained it, we gave it the answers and we gave it the data. We trained it using a bunch of leaves long before the plant became diseased. So we trained it with a bunch of leaves to say, you know, this is what this leaf looks like. We don't know if it's diseased yet. This is what this leaf looks like. We don't know if it's diseased yet. And then a few weeks later, these ones that became diseased, we had the pre-training data from them. And these ones that weren't diseased, we had the pre-training data from them. And we ended up building this application that would run on an old Android phone that doesn't require any kind of connectivity, that all of the inference that all the farmer has to do is wave it over a leaf on their farm. And now they can see this leaf is likely diseased or not. So they can rip that plant out and not risk losing the rest of their crop. No cloud connectivity required, cheap Android device, and it will run on that. Now, we're not all going to build cassava detectors, I understand that, but think about the scenarios that now become possible with this programming model that weren't previously possible. And one of the things I like to share about my personal history is I shared, like, those were the two revolutions. So when I first came out of university and I first started working as a software engineer, can anybody guess where I'm from, by the way? Ireland. Oh, wow. Nice. Most people don't get that right away. So, you know, I get a lot of Australian and whatever. And so, yeah, when I first came out of university, I was living in London and I was working in London, but I'm actually Irish. And if you know anything about the 1990s and being Irish in London, you know, there were two big issues. Number one was all the jokes about people being stupid and people being useless and people being drunk, you know, they were the Irish. And the second one, we were the terrorists. So, you know, being a software engineer working in London in the 1990s as an Irish person, the amount of discrimination that I faced was unbelievable. You know, I would go into some customers and customers would hear my accent And I actually had one example where I was working with a bank, and this bank were bankers to the royal family, and I went in and I was demoing this new thing that I was building, and the guy actually said to my manager, "Is he Irish?" And my manager goes, "Yeah." And he's like, "Get him out of here." Okay? So there was a crazy amount of discrimination, but the reason why I'm pointing this out is not to feel, oh, sorry, but more a case of that was at the beginning of the web revolution, and I was lucky enough to identify that and skill myself up in web skills to the extent that when people were really hungry for web skills, they saw through that discrimination. It allowed me to bust through that glass ceiling. Now, we spoke earlier on, Kyle mentioned women tech makers earlier on. Our industry, there's a lot of discrimination against women. There's a lot of discrimination against older people. There's a lot of discrimination against people of color, all that kind of thing. And I would just say, here is a great opportunity if you are suffering to skill up in something new, the way that I was able to skill up in something new. And hopefully the stupid people who have a problem with you and who you are will be hungry enough to see through that when they see your skill set. So particularly if you're women here, people of color, all those kind of things, this revolution could possibly be something that's wonderful for you to help you break through those glass ceilings. Okay, so moving on. So as I said earlier on, answers and data come in, rules come out in machine learning. So what happens? So in machine learning, you take your answers, you take your data, you feed them in, and you do something that I've mentioned a few times called building a model. That model is typically a neural network. And so I'm representing that neural network with these blobs. And then at runtime, once you have that model and you're running that model on a device or you're running that model on a server, you pass it data and it gives you something back that we typically call predictions. Now, it can be a little bit confusing when you use the term prediction because it often sounds like a prediction is thinking of something in the future. But in this case, it's an inference gives you a prediction. So the idea is like, say, for example, if you're doing an image classification, and I'm going to show later on, you probably saw me holding stuff up to the camera earlier. The idea is that it's going to kind of pick what it thinks it is, and we call it a prediction because it gives you a probability. It might say, hey, there's a 30% chance you're looking at a car. There's a 20% chance you're looking at a motorcycle, something along those lines. And that's why the term predictions tends to be used. But of course, this does lead to a misnomer that people think artificial intelligence is all about something predicting the future, predicting stock prices, lottery numbers, all that kind of thing. But it's not. The scenarios that you can build are far broader than that. So and another term that you use is, so when you're building a model by feeding answers and data in, we call that the training phase. And then when you're running inference on that, when you're at runtime, you call it the inference phase. Think of this like in traditional programming, when you're writing code and compiling, that's your training phase. That's when you're building your model. That's when you're building your application. And then when you're running that compiled code, we typically call it maybe executing, that's the inference phase in machine learning parlance. So at Google, to just give some examples of some stuff that we've been able to do with that, is that, some people who are, it doesn't really show up too well on this projector, sorry, but some people who are image processing experts were able to say, if you take an input image, and then I'm going to saturate that image, so you can see, for example, here, the background's nice and green, and here it's faded, and here the background's nice and colorful, and here it's faded. And if I do these things, and then I kind of defocus my image. So I say, hey, look, I'll build a portrait like this of this young lady and this young man and say, okay, I'm going to defocus. What I'm going to do is I'm now going to train a model to say, if you have this image, I want to see this. And if you have this image, I want to see this. And as a result, by training with thousands of images, they were able to come up with, okay, an input image that's defocused will go from that to that through a saturation tier. An input image that's defocused will go from that to that through a saturation tier. And that's then been built into the camera that runs on Android devices, so you can end up getting an automatic defocus. If you've ever done defocus on Android, you might remember you used to have to take a picture and then move a little bit and take another picture, and it would automatically do the defocus. And that was lots of if-then code. We've since changed it to a machine learned model, so now you just take a single picture and it will defocus it for you automatically. And another example is the smart reply in an inbox. If anybody uses this, it's pretty cool. So if you use the inbox app on Android and you want to reply to somebody, there are generally 3 options that you get. Sorry, it's a little hard to see right now, but you'll see this email, and before she writes this email, you'll see, once the keyboard goes out of the way, you'll see the 3 options: no plans, I just sent them, or I'm working on them. So it actually parses the text in the email that's sent to you, and based on emails that we've trained it on, and that's a lot of our internal emails that we use at Google. And then the replies that people have given, we've kind of come up with an intelligent way of saying, well, if somebody asks you, are you going to lunch today? the replies are probably going to be yes, no, or maybe tomorrow, something along those lines, and as a result get that auto reply. And we found that since we've launched this, about 10% of responses sent on mobile use it already. And again, if you're to do this with lots of if-then code, it's probably infeasible, probably too expensive. Google Translate is another one, and one of my personal favorites, where the idea is we used to do statistical-based translation, where the idea was if you see a particular phrase in a particular language, and then you have a whole bunch of source documents that say, well, 80% of the time this phrase is translated to this, 20% of the time it's translated to this. We'll follow the 80-20 rule and give you this translation, but then 20% of the time you're wrong. And instead of ordering sushi, who knows what you end up buying. And and the idea, again, to make that more feasible, to make it much more accurate, we're using machine learned models without all of the if-then rules. And that also, of course, as you can see in this example, works with images, which I find is pretty cool. But to be honest, if the exit is that way and the building's on fire, I'm not going to be holding my camera up and expecting the translation. I'll be running for fresh air. Okay, so one example that I've been working on personally that hopefully will help illustrate this from a programmer's perspective is there was an open data set around breast cancer that was done by the University of Wisconsin. And what they did was that they, remember, thinking in terms of answers and thinking in terms of data. So what they did was they put out this whole bunch of data about biopsies of cells, and they said, okay, these ones turned out to be malignant and these ones turned out to be benign. And each of these biopsies for each particular cell has about 30 different data points. Simple things like the size of the cell, more complex things such as the opacity of the cell. Now, if there's 30 different things about the cell, 30 different attributes, for me to write a whole bunch of if-then rules to try and figure out a way as a programmer of saying these ones are going to be malignant and these ones are going to be benign is kind of hard. But you might start with something like this, okay? Like I plotted some of the cells here and I plotted the radius of the cells. And hey, this was pretty easy, right? That the malignant ones are on the right and the benign ones are on the left. So I could kind of draw a line like this. And on this line, I would say, well, whatever that value is, if X is greater than that value, the cell is malignant. And if X is less than that value, the cell is benign. Great, let's fire all our doctors. All right? Not that simple, right? That's only one piece of data. So I say, okay, well, I take a second piece of data about the cell. I get something like this. And now my vertical line kind of doesn't work, because some of the malignant cells will be on the left of that vertical line and some of them are on the right of that vertical line. But I could also kind of maybe draw a line a little bit like this and say cells that are above and to the right of the line are probably malignant and cells below and to the left of the line are probably benign. Job done, right? But that's only two pieces of data about one of these cells. What if I plot it in, before I get onto that one, and then for me to code, it's really easy. We all remember our high school math, right, where the formula of a line is y equals mx plus c. Is that what you use in Canada? Do you use mx plus c? Or do you use wx plus b?
MX plus B, yeah.
mx plus b? Oh, so it's a hybrid of the two. So I went to school in Ireland and we use mx plus c, and then I show this in the United States and people go, what's m? What's c? Is that meant to be w and you got it upside down? So it's mx plus b in Canada. My goodness, every country has a different. We need an AI to kind of give me all of these. So your formula of your line is y equals mx plus c, and then you could write code easily to determine what's above the line and what's below the line. Easy stuff. But again, that's only 2 data points. Here's what happens when I plot it in 3 or 4 dimensions, actually. There's a 4, 3 dimensions. My data ends up looking like this. So there are actually 3 dimensions in this diagram because if you think about this as you're looking down the 3rd dimension, and you can see these blobs are bigger than, I got a laser pointer, I forgot, than these blobs over here. So it's like almost like you're looking down, these are closer to you, and the green ones over there are further away, which is kind of telling you that green cells the smaller ones are more likely to be benign, and the bigger ones are more likely to be malignant, that kind of stuff. But look at the mess in the center right here. Right, look at this mess here. How would I create a rule for that? And then if I zoom in on that, if I try to draw a line like this, it just doesn't work, right? And then if I zoom in, it's even worse because if I go back, I've zoomed in on this area here, and it ends up looking like this, and they're kind of spread all over the place. So the moral of the story here is if I'm trying to write if-then code for this, it's just not feasible. And we're talking about breast cancer here, right? We're not talking about the person's walking or the person's running. This is something really, really, really important to get right. So how does machine learning help with this? Okay, so let's go back to my one-dimensional example and think about this now from a machine learning perspective instead of an if-then perspective. So remember I had this line here. In machine learning, you probably hear the term decision boundary. So this is a decision boundary. Okay, and I say, okay, what would I do to figure out this decision boundary in just one axis? Say it would only work for one axis. I'm just going to take the simplest possible case. Well, the idea is that in machine learning now, what I really want to do is figure out this value, have a machine figure out what that value is instead of me telling it what that value is. And I'm going to call that a weight. So the idea is like, I'm going to input a whole bunch of values. I'm going to define like a little neural network, a layer in a little neural network. And this little neural network, its job is to figure out the weight, to figure out what that line would be. And, I have some data here and I'm going to label the data. And I notice that, hey, if the radius was 18, it's benign. If it's 31, it's malignant, these kind of things. And then there's something in machine learning parlance that you call an activation function. And every layer in a neural network has an activation function. And a common one that you'll hear about is called ReLU. Anybody know what ReLU stands for? Rectified linear unit, right? And here's where it starts getting all mathy. But the idea is, if you just think about this in programming terms instead of math terms, think about this as a function. If x is greater than 0, return x, else return 0. That's all it is. Okay? So now if I said, okay, well, what if I, set my activation function on my layer to be ReLU of radius minus 30? What's going to happen? I'm going to have a trained neural network right out of the box. My output is going to be 0 if the cell is benign, and it's going to be greater than 0 if it's malignant. And now I've built something, a very, very simple classifier that works on a single dimension of data. But as I said earlier on, we can't do it on a single dimension of data. That's kind of ridiculous. So what happens when we have multiple dimensions, like this one? Well, remember this line and the formula for the line? Okay, I'm in Canada, so I'll say y equals mx plus b. And so what if we could have a machine figure out from all of the data what that line looks like? How would we do that? Well, we do a very similar thing. Remember y equals mx plus b. So we're going to have a neural network with the job of one layer is to figure out m, and the job of another layer is to figure out c or b. And then my output for that, and once I have that line, and I know what that line is and that line works, now this model is going to be able to say what's above this line and what's below this line. So again, how does that work? Well, first of all, in machine learning, the idea is you throw random data at it to begin with. So I'm going to just throw a random m at it, and I'm going to throw a random b at it, and I'm going to get a line like this. And this line is really bad, right? Because a lot of benign data is above the line. And so this isn't going to be a very accurate model if I use it. So, but I'll start with that. So I'm going to say, hey, I'm going to start with m equals 0 and c equals 5. And what happens? So if you imagine m equals 0 and c equals 5. So I'm going to take all of my data that I have, and I'm going to segment a small part of that data. So say I've got, I think in the Wisconsin breast cancer data set, there's 8,000 pieces of data. So what I'm going to do is I'm going to take, say, maybe 2,000 of those and put them aside. And then I'm going to train my thing to say, okay, what happens when m equals this value? What happens when c equals this value? Give me an output. And then that output's going to say, this cell I think is malignant. This cell I think is benign. Okay, going to get my finished model with all of them. And then I'm going to get my test data, which I know the answers to. And I'm going to pass them to it and test my results against that data and see how accurate it is. And of course, I would get something like this, and it would tell me that my model sucks, right? Because, I'm testing it with a lot of data, and a lot of the data is wrong. So what happens is you then have another type of function called a loss optimizer. And the idea behind the loss optimizer is says, okay, your results suck. You've done really badly with this because your m isn't very good and your c isn't very good. But this loss optimizer function, what it's very good at doing is trying to guess a new value of m and a new value of c that won't suck quite so badly. Okay, so these loss optimizer functions, there's a whole ton of them. If you're a mathematician, you're probably familiar with them. The nice thing about something like TensorFlow is they're all built in. You just pick one. Like something like, for example, there's a thing called a root mean square error, or, there's atom optimizers, lots of other stuff like that. If you're a mathematician, you understand them like me. I'm not a mathematician. I don't understand them. But fortunately, as a programmer, it's just setting a property. And then the idea is what the loss optimizer will do, based on the test data that you give it, based on the results that it got from the values of m and c that you guessed, it will try new values of m and c and go through the loop again. and then it'll come up with the results, figure out where it went wrong, try new values of M and C, and then go through the loop again. And the idea is that every time you go through the loop, you get more and more accurate values of M and C. So if you can imagine again, like remember my first line was across the bottom, and then say maybe the second line, the loss optimizer would say, well, try this. And this is better, right? Now there's less errors. Now there's there's only a couple of errors, but it's really bad, of course. Why would these errors be really bad?
Somebody could die.
Yeah, because there's two here that I'd said are benign when they're really malignant, and you don't want to do that. So the idea is, okay, I have too many errors. So usually with and by the way, with this one I got something like a 98% correct rate, which is unacceptable, I think, for breast cancer, but I only spent a couple of days on it. And so the idea is, hey, look, try M equals 0, C equals 12, and you get something like this. My error rate is still too high, and then maybe you try another value and end up giving you something like this, where M equals -1 and C equals 20. So this is the process that's called training. So when you hear about training in AI and you hear about training in machine learning, that's all that's happening, is that you got layers trying to figure out values, you've got test data going in, the test data is compared against what the model actually said it should be, the amount of errors that you get against the known test data are calculated, an optimizer tries to figure out new values, feeds it back in and tries again. And sometimes you can do this several thousand times before you end up with a decent model. Like in the case of the breast cancer thing, when I ended up with the 8,000 pieces of data, and I trained for about 500 cycles before I ended up getting about a 98% accuracy rate. So that's why when you start exploring machine learning and you start exploring AI, you start hearing all these terms, you start hearing about training and all that kind of thing. And this is why it's important, so you can get your values correct. So now that was with just 2 dimensions. What happens when you got tons of dimensions like this? Okay, so that kind of decision boundary doesn't work, and you might end up with a decision boundary like this. And in this case, I've only got 3 dimensions, but your decision boundary for each, for X, for Y, for Z, all those kind of things might be in higher powers. But then what happens if it's in 30 dimensions or more? Think about how complex the math is going to be to figure out what that decision plane looks like, so that 99.999% are on the right side of the line and 99.999% that you want to be on the wrong side of the line are also there. The error rate is very low. The process is exactly the same as what I've just explained for 2 dimensions, but obviously the math is a lot more complicated, but you end up just doing the same thing. You got multiple layers, and their jobs are just to find out what the weights are, to define that line, to define what that plane in 30-dimensional space would look like, and give you that output. You give it test data, a loss optimizer tries to figure out why your test data sucks, or why your results suck on the test data, and as a result, recalculate new weights into it. So all of this is then done for you by a technology that we call TensorFlow. Oh, there was a missing slide there. So the idea is, this is what we do at Google. This is how we've built a lot of our systems. And then the technology that we use for that, we open sourced back in 2015, and we call that TensorFlow. So the idea behind TensorFlow is it allows you to define all these layers, allows it for you to define your networks. It's got a whole bunch of loss optimizers pre-built, so you can just pick it. It's got a whole bunch of activation functions like ReLU that I mentioned earlier on that you can pre-built, so you can just pick them. And as a result, you don't have to be coding all of this for yourself. You design your layers, you design how they work, you throw your data at it, you train, and see what ends up coming out. Now, one of the more exciting parts about this, and part that I've been working on then, is what happens then with mobile. Think about the farm in Tanzania example that I spoke about earlier on. And so when it comes to mobile developers, there are a lot of confusing options available to you. So I'm going to try to demystify them a little bit. So first of all, if you want to think in terms of, there's Google Cloud AI. So I'm going to just show everything just to make it a little bit clearer. So there are connected scenarios and there are disconnected scenarios. So my farm in Tanzania that I was talking about, where these people waving their phone over their plant, they don't have any kind of cloud connectivity, so all the inference needs to be done on the device. That's a disconnected scenario. But of course, there are also connected scenarios, and the advantage of that now is if you can connect to the cloud, then there are services that are pre-built and designed to scale that are available and have been built for you. And a bunch of these are in Google Cloud. We call it Google Cloud AI. And so things such as video intelligence, that it can look at a video stream and start tagging the things that are in that video stream. So for example, I don't know, you may have a CCTV looking at a road and you only expect to see cars on the road, and maybe it sees a bicycle on the road and you want to raise an alarm that there's a bicycle on the highway. Something along those lines. That's what video intelligence is all about, tagging what's in a video stream. Cloud vision is very similar, but it's for a single frame. So the idea is you can pass it a single frame and it can tell you what it sees. And then there are a number of things that it's designed to detect, such as landmarks. So if you ever use Google Photos, sometimes it goes, oh, that's a picture of the Eiffel Tower. That's how it's working. You know, it's been trained to recognize certain landmarks or logos or other things like that, common things that you might expect. There's cloud speech recognition, where the idea is you pass it an audio stream and it comes back and says, this audio stream says blah, 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 which you can then use in translation or whatever. Text to speech, the other way around, you pass it text and it gives you back speech. And then, of course, translation, which I spoke about earlier on. So these are services that work in a connected scenario that you might be able to build something around yourself. But of course, because they're pre-built services, they're limited. You know, the Cloud Vision, for example, is limited to the images that we have trained it for. But you may have scenarios of your own that you want to recognize different images. For example, you are a banana farmer, and you have 20 different species of banana, and you want it to be able to recognize the difference between your 20 different species of banana. Then the idea is, well, our Cloud Vision will tell you it's a banana, but it won't tell you what type of banana it is. And that's the idea behind Cloud Auto ML at the bottom left here. And then the idea there is you can take our existing vision models, and then you can build on them based on your specialty. So if you're a banana farmer, you'd use Cloud Auto ML to build your banana species detector or whatever it would be, you know, in AutoML. Same for natural language, same for translation. For example, translation might work very well in common scenarios. Can you show me the way to the beach? But it may not work very well in other scenarios. Can you tell me the difference between an autoencoder and a ReLU function, please? You know, translation may not work very well in that. But the idea is if you've got a specific domain and you have expertise in that domain, then you could retrain our translation, build another layer on top of our translation in order to have your specific translation for your specific domain. And that's the goal behind AutoML. So that's connected scenarios on the left. For disconnected scenarios on the right here, so any Firebase users here, by the way, out of interest? Okay, cool. Firebase is really neat. I used to work on Firebase, so I'm biased. But it's really neat for mobile developers that a lot of common scenarios that mobile developers do have been implemented in Firebase, things like sign-in and messaging and various data scenarios. And following that philosophy, what the Firebase team have done is they've taken a lot of the connected scenarios and made them much more approachable for mobile developers. So the Firebase programming model, the asynchronous programming model of Firebase, and being able to deploy and manage on mobile devices for a lot of the things. And you'll see there's an almost one-to-one mapping between MLKit and the Google Cloud AI. So things like text recognition, face detection. Please note it's face detection and not face recognition. You know, we're very careful that we're not in the business of face recognition, but we'll help you detect faces. So for example, if you want to know if there's a real person in a picture, or maybe smile to take a photo or something along those lines. Barcode scanning, image labeling, and then the ability to host custom models are all part of what's called MLKit from Firebase. So that's yet another AI machine learning offering for mobile developers. And then finally, what I work on, and that's TensorFlow and TensorFlow Lite. And the whole idea is that's trying to get a little bit closer to the metal. So if you have a model that you want to define for your scenario, for example, I was working on the breast cancer stuff, then the idea is TensorFlow Lite is designed for that. You can build your model using TensorFlow, you can execute it on TensorFlow Lite, or if you really like the Firebase programming model, you can host it in Firebase MLKit and then run it there. Okay, so going back, remember the training phase, that's TensorFlow. So giving answers, giving data, and inferring rules, machine learning, that's what TensorFlow is all about. You program TensorFlow typically using Python, but we also support new languages like JavaScript and Swift and Go and Java and that kind of stuff. But 99% of the stuff you're going to see in the actual training is in Python, because that's the primary language used by data scientists today. We just recently released Swift, and we're still working on Swift, and there's a lot of interest in that. And like I also mentioned, JavaScript. JavaScript is actually really cool because then you can do training in the browser, as opposed to needing a centralized machine on which to do training. So you might be able to distribute to all of your users via the browser, collect data for training a model from all of them, or maybe even train mini models for each of your users and send them back to the mothership and then train a master model off of those. Something along those lines. That distributed scenario is what it's all about. But that's what TensorFlow is. So think about TensorFlow as the engine that you use for building models. In typical programmer parlance, it's the code you use for writing and compiling your actual executables. TensorFlow Lite is then what you can use only for inference. So if you want really, really fast inference on mobile, if you want really, really fast inference even on a PC, or increasingly we're working on edge devices and IoT devices, then TensorFlow Lite's all about that. So you give it the data, it'll infer something for you, and it'll give you a prediction. So how does all this work? What's the difference? So on your workstation, you'd use TensorFlow. Remember I spoke earlier on about training and how much math there is and how much you got to go around all those loops. That's really, really intensive of processor time. So there's your main workstation. There's basically three things it can execute on. Number one is we all have a CPU. Number two, maybe some of us have a GPU. And then number three, there's a new thing called a TPU. So if I talk about it in those terms, so first of all, the CPU, I like to think of as a Swiss Army knife, right? It's designed to do anything. Everything on your PC, from managing the keyboard to the network stack to everything, the CPU does that. The GPU was designed as something with lots of little cores in it, and all of these cores can work in parallel, and all these little cores work in parallel to do lots of math operations that you can use for 3D games, right? So 3D games, two of the main things that they use, floating point calculation and matrix multiplication. And entirely coincidentally, these are two of the things that are heavily used by machine learning. All that cycle that I was talking about earlier, all the math that's in that cycle uses a lot of matrix multiplication and a lot of floating point operations. And as a result, GPUs are really, really useful for your training phase. So instead of if you want to train a model, instead of you taking 24 hours to train the model before you can test it, maybe you can use a GPU and you can do it in an hour or less. And then finally, there's something called a TPU, and this is a tensor processing unit. And TensorFlow, the name isn't a coincidence. TensorFlow was designed there's a mathematical construct called tensors, and a lot of our math is built using tensors, and the TPU, the tensor processing unit, is optimized even further for them. So if your CPU is a Swiss Army knife, your GPU is like your bread knife, and then your TPU is like a sushi knife. It's highly optimized for one specific task, and as a result, training can be much, much faster on a TPU. So on your workstation or in the cloud, you would build your model. And then for TensorFlow Lite, the idea is you then convert that, you flatten it, and you shrink it so that it's optimized for mobile. And then you can run it on mobile using TensorFlow Lite interpreter. Any iOS developers here? I'm sorry. No, I'm a big fan of iOS. I actually wrote a book on iOS development, and then Google hired me because I wrote that book. I think they just wanted to take me out of the iOS community. So I always get the question from iOS developers, what about CoreML? And CoreML is great, but CoreML is a totally different ecosystem. But what we wanted to do is we didn't want to exclude CoreML developers, even though TensorFlow Lite runs on iOS. We didn't want to exclude CoreML developers. So as part of the process of converting your finished model into TensorFlow Lite format to run on TensorFlow Lite, you can also convert it to CoreML so it can run on CoreML should you want to do that. Okay, so let me show some code. And here's a really simple example of how you would build what I consider to be like a hello world in machine learning. So first of all, I'm going to remember my diagram earlier with my layers? So I'm going to create a very simple layer here. When it says sequential, that means the layers all follow each other. And it's just going to be a single layer with a single neuron in it. And then, if you remember each layer, there's something for optimizing it, optimizing the math on that, various ways you do it, and then for calculating the loss on that. So I'm just going to say that. Okay, I'm going to compile my model, and I say I want the optimizer to be SGD, which is stochastic gradient descent. Again, math. You don't need to understand that now, thankfully. And then my loss is the same thing, mean squared error, math. But I don't have to code all that. I'm just specifying it as a property. Okay, so now I'm going to say, I'm going to train this on some data. Okay, I'm going to give it a set of inputs, and I'm going to give it a set of expected outputs. So here, if my inputs are -1, 0, 1, 2, 3, and 4, my expected outputs are -3, -1, 1, 3, 5, and 7. Can anybody see the relationship between those two sets of values? What's the relationship between y and x? Very good. All right, so y equals 2x minus 1. What you've just done is figured out the relationship between the two of them and expressed that as a formula. And that's exactly what machine learning is. This programming is all about teaching a computer to do exactly what you did. Remember we said artificial intelligence is emulating human intelligence. Amin is a very intelligent person. And so now I'm just writing code so that it can emulate his intelligence in figuring out that formula. But with a computer, I just do that by throwing, here's my set of data, here's my set of expected outputs, try and figure out what the formula is to do this. And to do that in machine learning parlance, it's called fitting. So I just say model.fit, here's my inputs, here's my outputs, and go around 500 times. Okay, so I mean, that could be anything. It's really up to you. The higher the epochs, the longer it takes to train. The lower the epochs, the less accurate it is. But I just picked like 500 epochs here. And then if I say, okay, well, model.predict 10. So remember, I'm just giving it a single input, 10, and it's going to give me an answer. What would the answer be? 19, right? It usually gives me about 18.97, right? Because it's only been trained with very little data. It's only like 6 data points. The more data you have, the more accurate your model will be. We're guessing just on the data that we have that it's y equals 2x minus 1, but we do live in a quantum universe, so who knows? And so now what do I want to do is like, okay, if I want to run this on mobile, what am I going to do is I'm going to save out that model, that compiled model, because I was using something called Keras. That compiled model gets saved as a .h5 file. And with TensorFlow, I just say, by the way, this is all Python code. With TensorFlow, I just say, okay, save out that model into that file. And then I'll say, okay, I want to convert this to TF Lite to run it on Android or iOS or an edge device. I'm just going to use something called a Toko converter. And the Keras file that I saved out earlier on, I'm going to do a conversion from that. I'm going to call converter.convert. And then I'm going to save this out as linear.tflite. Okay, and that's it. So what I've done is in Python, I've given X and Y data, I've trained a model, I've saved that model out, I've converted that model to a .tflite file. So now on Android, what do? Well, in Android, I've highlighted the wrong thing here, so let me focus here. Remember, I saved that as linear.tflite. If you're familiar with Android Studio, all I'm doing is taking that model, the linear.tflite, and putting it as an asset. So now I have that asset. What am I going to do next? A nice big red arrow there to show me. Now I'm going to, in build.gradle, I'm going to say, I want to use TensorFlow Lite. So we're all familiar with build.gradle. In iOS, you just use a pod. We have a pod for TF Lite as well. But in build.gradle on Android, I'm just going to say my implementation is org.tensorflow.tensorflow Lite version. And then in my Java code in Android, I'm going to import the interpreter. And then I'm going to say my interpreter, I'm going to pass it the model file. So load.model file is just a function where I'm loading that file out of assets. And I'm just like the pointer to that file. I'm going to send to interpreter. And then I'm going to give it my input value of 10, if you remember earlier on. It's a little bit weird in TensorFlow that it deals with tensors. And if you think of tensors a little bit like arrays of matrices, n-dimensional matrices. So if I want to pass it a single float, I'm actually passing it an array of floats with just one item in it. So that's why I define it this way. My input value is an array of floats with a single item in it, and I'm going to set the value of that single item, which is index 0, to be 10. And then on TF Lite, I'm just going to say, for my output, first of all. So TensorFlow Lite's going to write stuff back to me. I know it's a float, but just in case it isn't, the easiest way for me to do this is if I use a buffered reader or a byte buffer in Android. And because it's a float, I know it's going to be 4 bytes. So I just want to read those 4 bytes back. And then tflite.run. So I called tflite, and remember, is the new interpreter that I created on the second line. So when I run that, when I call the run method on that, I give it the inputs. I pass it the outputs where I want it to write, or the output val. It will write into the output val, and then I can read out of that. And if you use byte buffers, it's kind of weird in Android, but you got to flip it when you're reading because it writes in one direction and reads back in the other. So I'm going to flip it, and then just my float that I'm going to get back is output val.getFloat. So that's going to be, I'm passing it in a 10, and it's going to give me back like 18.97, something along those lines. But that's all it is to execute. So first of all, to train, flatten, convert, and then execute a model on Android using TensorFlow Lite. It's pretty cool stuff. So I'm going to give a quick demo of this. Are we good for time? Yep. 10 more minutes. Okay, cool. So I'll have time for Q&A. Need to find my mouse. So I'm going to give a quick demo of this. It's a little hard to do this, but so I am not a bathtub or a dumbbell. So the idea is that this is the demo app for TensorFlow Lite. And what we've done here is there's a common image recognition model called MobileNet, which recognizes 1,000 different class of image. And what this application does is it's reading from the webcam. Hello. It's reading from the webcam, and then frame by frame, It's calling the code that I showed earlier on, passing that to the model, which has been flattened, and then it's recognizing that as a probability across these 1,000 different things. So right now it's seeing like a 0.87% probability that it's a projector, a 0.03% probability that it's a spider web, and then taking across those 1,000, remember I said it calls this a prediction, and across those it takes just the top 3 and renders them, and then also shows us how long it actually took to do that. So even though I'm running this on the Android emulator on my Mac, if you can see really, if you got good eyesight, you can see right here, it's usually like 500 or 600 milliseconds to actually run it on an emulator on the Mac to do that inference. And anybody fans of Silicon Valley? Remember Hot Dog or Not Hot Dog? They built that using this technology. So I brought my hot dog, and I have a reputation for teaching using a banana, but it's not working very well tonight. There we go. We had banana there for a second, but bathtub. It's not a bathtub. It gets confused by the background sometimes. If I put my face, what does it say? I've gotten coyote, I've gotten everything, but it's, you know. Oh, banana! There we go. It was just delayed. Bad computer. Okay. So again, this is all open source code. It's available on TensorFlow.org, and there's a code lab called TensorFlow for Poets. And that takes you through all the steps of downloading the MobileNet model. It was built by some researchers in Stanford. And then you can then flatten that and then use the Android code, Java code on Android. And there's also an iOS version. Right now, TensorFlow Lite on iOS only runs in C++. So if you're an Objective-C or Swift developer, you got to use C++ just for that inference part. But we're working on Objective-C and Swift libraries, but they're coming soon. Okie dokie, now if I can go back to my slides. There we go. Okay, so just going back to the beginning, we were talking about AI, what AI is, and hopefully this has helped cleared it up a little bit from a developer's perspective. Remember, if you're building something that's artificially intelligent, the idea is you're building something that emulates what a human does. Now, this could involve traditional programming. This could also, and more often, this should also involve the kind of machine learn-based programming that I'm talking about. So machine learning is the idea is like you can make machines learn from explicit examples instead of from you actually writing code. And then there's a new thing called deep learning, which is similar to machine learning. But one of the neat things about deep learning is, remember earlier I was like saying, for example, for a watch like this, when I say this is what walking looks like, this is what running looks like. When you're with deep learning, the machine is actually smart enough to figure even that part out for itself. It's smart enough to figure out and label the data for itself. And so this term is, more and more interesting in the research space. But for the majority of what you're going to be doing as a programmer right now, you're probably more in the green blob there in the machine learning area. So thinking about creating your data, tagging that data, labeling that data, and then training models to run inference on that data instead of you writing all these if-then rules to classify that data. So strong AI or true AI or general AI, those kind of terms that we're talking about, that's the kind of application that you build that runs in the blue space there. Then it's going to be using, like I say, traditional code. It might be using machine learn code, and it may also be using deep learn code off of the machine learn code. So I don't know how well the sound is going to work here, but I want to show the cassava video. And let's see. If you can't hear it, I will share it with you online later.
Cassava is a really important crop. It provides for over 500 million Africans every day.
When all other crops fail, farmers know that they can rely on their cassava plants to provide them food.
There are several diseases that affect cassava, and these diseases make the roots unedible. It is very crucial to actually control and manage these diseases.
So we're trying to use machine learning to respond to those diseases.
And TensorFlow is the best foundation for our solutions. The app that we've designed can diagnose multiple diseases. It's called Neuro. It's what we leave the light that farmers can use to see their problems and find solutions. You wave your phone over the specific leaf, look at it, and if it has a symptom, a box will pop up saying you have this problem. When you get a diagnosis, we have an option for you to get advice and learn about the best management practices.
The object detection that we use through TensorFlow relies upon our team annotating images.
We've collected over 5,000 high-quality images of different cassava diseases for this project. We use a single-shot detector model on a mobile net architecture. It's able to make predictions in less than 1 second.
Instead of having to implement thousands of lines of code, TensorFlow provides a library of functions that allow us to build architectures in much less time.
We need something that can be deployed on a phone without any connection. TensorFlow is able to shrink these neural networks to be able to fit on your mobile device.
The human input is absolutely critical. We're really building something that augments your experience and makes you better at your job.
So with AI tools and machine learning, you can improve the yields, you can protect your crops, and you can have a much more reliable source of food.
AI offers a prospect to fundamentally transform the life of hundreds of millions of farmers around the world.
You can see a product that can actually make someone's life better. This is kind of revolutionary.
So the way the emergence of the web gave us the likes of Google and Amazon, and the emergence of the cell phone gave us the likes of Instagram and Uber, and all these new industries, that there are new industries out there waiting to be built, and the opportunity to do that is now. We hope that we have the framework that will help you to do that. And with that, I just want to say thank you very much, and I can take questions. Any questions? Amin?
How do you prevent overfitting of the model?
Wow, we're going right into the detail right away. So, how do you prevent overfitting? That's a really good question, and the only answer that I can give, unfortunately, is it depends. So overfitting is that when you are training and you're focused too much that it's 100% accurate on the data that you know and unknown data that you just don't know, and you end up like, yes, it works perfectly. It works on my computer, that kind of thing. The only way that the technique that we use is constant retraining. As you have new data, there's constant retraining. There are various mathematical models that you can use to statistically analyze your data and say there's a good chance that we are overfitting. But unfortunately, it has to just be done on a case-by-case basis, and typically, constantly retraining your models as you learn new things. So over here.
Right. For this project here, is there a requirement to always be a couple of inches away from the leaf to get consistency, but you don't want to back up?
Okay.
Will that be?
That's a really good question. So talking about the cassava project, do you have to be close for consistency? My understanding is yes, that the image of the leaf has to be a certain size, and of course it has to be in focus for you to be able to use it. I don't know the specifics of that, but in general, yes, you would have to be a certain distance away. So do you see any problem with that, or would there be any kind of restriction, or?
No, well, it's just an application that
Okay.
I'm working on for a client. So I saw their example that we put the leaf stand on the edge.
Right.
Maybe they say, it's had an edge of it.
Yeah. So, I mean, the only rule of thumb that I would say is that when you want to do the classification, that the data that you're classifying has to look like the data that you trained on. So if you always trained on a full frame leaf, your classification would have to be on a full frame leaf. If you increase the size of your training set, so you do all those different edge cases and that kind of stuff, then your classification in those would also be improved.
So you one with the full plant on the leaf.
Yeah, something like that. Exactly, something like that. So behind you here, yeah.
Did you think anything about the on-premise software, how you can use the TensorFlow when you actually do not have data as a part of your software, but when you deploy software on somebody else's environment and they control everything on their side? So does TensorFlow provide anything for that kind of environment?
So there are stuff that we're working on that. There's the first thing is we built. So the question was if you are building TensorFlow models and people want to deploy them on premise and anything for managing that. So we're working on a whole bunch of stuff in that. The first thing that came out of that is something we call TF serving. So the idea is that it's a serving environment to handle serving models and managing different model versions. As for like Amin's answer earlier on, that continually training and you get new versions, you end up in a situation similar to continuous integration and continuous deployment. So we have a framework that we're working on. We're going to be announcing a lot of that just next month, so I can't talk about too much detail about it now. But there is a whole bunch of stuff coming down the pike, the first of which is like TF serving. Okay, over here.
So when you go from TensorFlow to TensorFlow Lite, I presume that the size of the model gets like really small, right? So how much precision or like quality of the model are you losing in that sense?
Right, so the question is, when you're shrinking a model from TensorFlow to TensorFlow Lite, what do you lose, right? So the amount of precision that you lose will vary from model to model. You're reducing the number of decimal points on floating point calculations, and we do something called quantizing.
So can you control that, kind of like define how much you're willing to lose? Because like you can compromise on the size.
Right now, no. Right now there's a fixed formula, but that's a really interesting feedback that maybe we should have some kind of dial that you control how much you lose. But as of right now, it's a case of we've done a number of retraining of models ourselves, image models that we use internally in Google and other models that we use internally in Google, and we formulated a tool for what was optimal for them from a model size accuracy ratio, and then we just use that everybody can use. But yeah, the idea of having a dial would be really good, but there's nothing like that right now. So there was over here. Yep. Sorry.
For the Wisconsin tumor data set,
yep.
Did anyone manage to find like a reliable solution?
So for the Wisconsin breast cancer data set, there's a whole bunch of solutions out there. I think there are some really good ones on Kaggle. I'm continuing to tweak on it myself. If you're not familiar with Kaggle, K-A-G-G-L-E, it's a website that has lots of data sets out there, and they run a whole bunch of competitions, and then people post their results on there. And I think some folks have done it with the breast cancer data set. So it was over here.
For the TensorFlow Lite and the mobile environment, did you actually port in this serving model stuff? Because you showed here that the models are being accessed afterwards in Java on Android, and this stuff is being done in Python, right?
Yes, so so what I've showed here when I was showing the image classifier, what that was, there was an architecture called MobileNet, or a model called MobileNet, which was been trained to recognize 1,000 images. So we flattened that to run it on TensorFlow Lite. And then what I was showing was that with a Java wrapper around it. And what that Java wrapper was doing was pulling frames from the webcam, passing them to that, getting the inference back from that, picking the top 3 of them, and then rendering that on the UI.
Part with versioning stuff of models and
yep.
It's going to be the same as on the Google platform?
Hopefully, eventually, yes. Right now, all the stuff for versioning models that we have is entirely for web deployment and all that kind of stuff. On Android, you're going to be doing it manually. But if you're using the Firebase ML kit, I believe if you put custom models in there, it will handle the versioning of them for you. But I just did it manually here. Right. Any more? Right at the back.
How do you think deep learning would affect developers' jobs or their future?
So the question is, how is this going to affect developers' jobs in the future? I always go by those that don't learn from history are condemned to repeat it. You know, so if you stayed as a Windows desktop developer when the web revolution came, you know, then your options were limited. And if you stayed only as a web developer or something else when the mobile revolution came, your options were limited. I see this as a similar kind of thing. I see this as an opportunity to enhance your skill set. And eventually, there are skill sets of today that may become deprecated and replaced by this kind of thing, but that's an eventual thing. You know, we still have JavaScript developers today. It's still the most popular language there is, you know, even though in many ways it has been, you know, superseded, if for want of a better term, by other languages. But JavaScript never went away. Java never went away. And C#, any C# developers here? There's a few. Okay, I was a big C# guy too, you know, that kind of stuff. And I ended up like, now it's Unity are using C#, right? You may not be building any more Windows Phone apps. Any Windows Phone developers here? See? You know? But you can still use those skills in Unity. And I see it as the same thing. This is a new, I see this, even though it's a revolution, but it's a new tool for your toolbox because it will enable scenarios that you couldn't previously do. In the same way as once you learned Objective-C for iOS development, when the smartphone revolution came along, that gave you scenarios that you previously couldn't do. Android and Java, and now Kotlin followed. But to me, that's the opportunity. And as with anything in software development, you have to continually learn and continually update, or you eventually become deprecatable. And so this is the new thing to learn and update so that you aren't. Question here?
So all of these different examples, we talk about all the positive sides of how it could improve our lives, but any technology that has its own downsides as well and negative aspects.
Correct.
And in particular, what I am personally concerned about is how far do we go until we realize this industry or this particular thing, we should not be implementing AI into it.
Yeah.
For example, let's take the aviation industry, where we have seen now pilots sleep behind the wheel just because technology does most of the work for them.
Yep.
But we have seen time and time again where accidents have happened, catastrophic failures have happened.
Yep. I think your pilot's example is a great one. So the question was like, where do we draw the line when we don't do this anymore because it's too dangerous? I think it's the same as the application of any technology. Your pilot's example is a really great one because autopilots are so great now that some pilots are getting drunk and some pilots are sleeping behind the stick. That is, again, it's a case-by-case basis thing. You can't regulate C programming because autopilots exist, right? In the same way, I don't believe you can regulate AI programming because whatever scenario exists. The one thing that's very different about this that I found though, and maybe it's because of the fear that I spoke about at the beginning, is that there is a lot of regulation and a lot of thoughtful stuff going on behind the scenes in big companies such as ours for how we're going to build a technology for scenarios that people can do. You probably saw on the news the internal issue that we had with drones and stuff like that, and people maybe a project called Maven that people may be able, or military may be able to do things with drones, and we are not in that business. And so drawing that fine line is going to take some time. We did draw up a set of AI principles, that we wanted to put a stake in the ground for the industry, and hopefully others will either help us adapt them to make them better, or others will adopt them. And I can't imagine the first draft of anything is perfect, and it's just going to take time. But I see it, like I said, like any other technology. It has good uses and it has bad uses, and at the end of the day, it's not about the technology that makes it bad, it's about what people do with the technology can make it bad. And we really just want to encourage people as much as possible to do the right things with any technology. Traditional programming, just the same as, you can build a centrifuge that, refines uranium so you can build a nuclear weapon by writing C code. It's got nothing to do with like the code itself, it's got to do with your intent. And, so we are walking that fine line, but we're trying to be as thoughtful as we can, thinking about the extra power that this gives and how that power can be misused. I think it was Spider-Man's uncle said, with great power comes great responsibility. And we're trying to have as much responsibility as we can, but we're not the world's policemen, right? We're trying to give people tools that will allow them to do great things and encourage them not to do bad things. Don't be evil. Yep.
You have shown the example for the emails where you had auto reply suggestions, I think.
Yep.
Are you aware whether Google is working on code automation tools? So you would have an IDE or coding tasks where it would also automatically generate the answers for you or help you programming? I can imagine that there are so many programmers in Google that this would really help you, right, to apply AI to computer programming.
So are you asking us, are we writing like APIs that will give you those kind of auto-response texts?
No, I mean rather like having an AI that partially writes programming code for you.
Oh, I see. Okay. That will really make us obsolete, right, when the AIs write the code. So the answer is yes and no. So I'll give the yes part first. That just to confuse things, there was a thing that we were writing, we originally called it Learn to Learn, and then we called it AutoML, and then we released a product called AutoML, which is completely different. But the idea behind Learn to Learn is that, earlier I was showing, hey, look, you got all these layers in the neural network, and you're going to put this activation function on this one and this loss optimizer on another one. You design it in a certain way, and then you train it like, with 10,000 loops, and you take a look at your errors. That process can be automated. You can have a machine come up and say, okay, try this design a neural network, try this design a neural network, try this design. And we've actually been working heavily on that in a project that we called Learn to Learn. And so in that sense, it's a yes, that will come with, but the expensive computation of that right now is sky high. It's infeasible, but you know, Moore's law and all that kind of stuff. So right now we're working on that. When it comes to traditional programming and computers writing code, that was actually something that was attempted many, many, many years ago, even before AI, and was generally rejected because there were some research done where it's like, okay, I write this piece of code, and my compiler can tell me that there are bugs in the code. Well, if it can tell me there's a bug in the code, why doesn't it just fix it? But there's more than one fix to every bug, right? You know, that kind of stuff. And it ended up by having all of these tools to help you rewrite your code and all that kind of thing, ended up making code even worse and was generally rejected by developers and rejected by the research community. So when it comes to rewriting Java code and all, or C code or anything like that, there's not a whole lot going on in that space because it was tried and failed a long time ago. But like I say, when it comes to designing neural networks, there is a lot of stuff going on in that space. And I mentioned diabetic retinopathy at the beginning. One of our models for diabetic retinopathy analysis built by Jeff Dean, actually he's been using that. So he kind of designed the initial model and then had something that continually refined the model automatically by saying, why don't you try a layer that looks like this, see the results. Try a layer that looks like this, see the results, that kind of thing. So yes and no is the answer. Okay, one more question here.
Just a comment to your remark. It would be kind of cool to create some sort of app that would pretend you're working.
I can tell your boss isn't here tonight.
No, I have to be smart enough to fool the boss too.
So maybe time for one more question before Kyle takes over. Yep, here in the yellow.
So just a question about getting started.
Yep.
So I think Google offers a lot of like learning materials.
Yep.
And I guess you need like
how to navigate them.
Yeah, and I hear you need a lot of data. Like one fellow was telling me about how he had like a cluster and they used like 300 gigs and several days and they still couldn't build.
Okay.
Like can you get started with like a GPU? Like,
oh yeah, absolutely. So my recommendation to get started, three things. First of all, tensorflow.org/tutorials. And on there are 5 notebooks. So we run an environment called Colab, which is a little bit, are you familiar with Python? So you know Python and Jupyter notebooks that you can execute Python in the browser. So we run an environment called Colab, which is very like a Jupyter notebook that you can execute in the browser, but it uses our cloud on the back end, including GPUs. So there's 5 things that you can step through there, including one of them is a really cool one. There's a data set called Fashion MNIST, where the idea is there's this whole bunch of data of different fashion items, shoes, t-shirts, jackets, and then you can train a model to recognize those. It gives you the data sets and it gives you all the code for training the model, and you just step through the notebook. It's really, really cool for learning. And there's 5 of them on there. There's another one for text classification where there's a data set of IMDb reviews of movies, where it has the text for the movie review and a tag saying it's a positive or a negative review. And then you can train on that. And then you can write your own movie review and it will tell you that you like the movie or you hated the movie, something along those lines. So the data's in there and the code for training is all in there. So that'd be the first thing I'd say is tensorflow.org/tutorials. The second thing is there's a book by a guy called Francois Choilet, which is, I think it's called Deep Learning in Python. And Francois is the inventor of Keras. And Keras is the language that I was showing earlier on for designing neural networks. Keras is a first-class citizen in TensorFlow. Francois actually works for us now. And his book is absolutely fabulous for learning this stuff. And then the third one, once you've done those 2, and then you really want to start getting a little bit deeper, is there's something called the Machine Learning Crash Course from Google. And this was something that we made public about 4 or 5 months ago. And what was neat about that one was that was a course that we designed to teach people who work for Google how to do machine learning. We have a commitment that every engineer in Google should have some understanding of machine learning and how it works. So we had a whole bunch of engineers design this course. We realized it's a really good course. It does have a lot of advanced topics, and we thought it's better for the rest of the world to know that too. So tensorflow.org/tutorials, I would start there. I'd read Francois Choilet's book, Deep Learning in Python, and then I would look at the Machine Learning Crash Course. All right. And the keras also includes a whole bunch of data sets built in, like the fashion MNIST and the IMDb stuff. So you don't have to go and get any, you don't need a big cluster. You can just do everything in the Colab, and we'll give you the GPU time to do it on. So. Okay, one more question at the front here.
I know that you have like TensorFlow for JavaScript as well.
Yes.
So, like for that one, do I need to know any Python to do that, or it is like only JavaScript?
Okay, so the question is, we also have TensorFlow JS for that one. Do you need to know any Python, or is it only JavaScript? You can do it in only JavaScript. You can do training of models and all that in only JavaScript in the browser or on Node. If you go to youtube.com/TensorFlow, I recorded a video series showing how to do that. So there's a public data set on iris flowers, where there's like a whole bunch of data points about iris flowers and which there's 3 different species of iris and which one it is. And then I show in a 3 video series, like, here's how you load that data set into JavaScript, here's how you turn that into tensors, here's how you train, and then here's how you infer. So it can entirely be done in JavaScript if you want. Typically, you'll build a model on a big fat TPU or GPU or something like that if it's a much more complex scenario. And for that, you need Python. And then that model you deploy to the browser and run the inference on JavaScript. But if you wanted to run in JavaScript, you can do so. You know, right now. Okay, so any more questions I can answer later on? I need to hand back to Kyle because we're running low on time. So thanks, everybody.